All right, we start this next section, the first section of Chapter 7, which is integration by parts, which is a really powerful technique of integration. I would say that it is on par with U substitution, maybe slightly more sophisticated and not as general as a substitution method. Integration by parts, however, is extremely useful both theoretically and in application. So the basic idea behind integration by parts is we have, there's a couple different perspectives you can take, as with anything. I would say there's two main ways to think about integration by parts. One is the most general way to think about it, and it's also exactly how I think about U substitution. You have an integral, that's hard, and you want to rewrite it into an integral that is easier to compute. The main difference with integration by parts such as substitution, like U substitution or any other form of substitution, the basic thing here is we're not actually changing variables. So with the case of U substitution, we choose, let U equal blah, blah, blah in our function, in our integrand, and we can then rewrite the integral into a new integral, and we've got a completely new variable, U, in that case. With integration by parts, we're not actually changing variables. So if we start with x, then the integral after we perform integration by parts, right here, this new integral, is still in the same variable that we started with. So that's the more general way to think about it. More specifically, I think of it as you have two functions that are being multiplied together. You can think of integration by parts as sort of like a product rule for integrals. It's the closest thing we get. In fact, integration by parts really is just taking the good old-fashioned product rule for derivatives and then rearranging some terms and changing the notation of how you write things. Okay, so the formula for integration by parts is you start with an integral, and then you say, okay, in my integrand, I am going to say part of it is U, and then the rest of the stuff, including the differential, is going to be assigned to dv. Then, once you know what U is equal to and what dv is equal to, you can easily find du from U by differentiating what you have for U to get du, and then taking your dv and integrating it with respect to x, and that would give you v. Once you know what u, v, du, and dv are, you can fill out this right-hand side of the formula, and you're good to go. So from a utilitarian point of view, I would think to use integration by parts when we're presented with an integral where the two things being multiplied together, x and e to the x, are very different kinds of functions. So for instance, we've got a polynomial kind of function times an exponential. So it's not like we have exponential times exponential or polynomial times polynomial. We've got these two very different classifications of functions being multiplied together. You would also think of maybe e to the x natural log of x, or maybe e to the x sine of x, or x to the fourth natural log of x. Anytime you've got this mixture of two very different kinds of functions being multiplied together, integration by parts is a natural choice. Now, that doesn't mean you have to have a product of two very different functions to use integration by parts. This formula up here is always valid, no matter what u and dv are. This formula is always valid. Just because a formula is valid doesn't mean that it's going to be useful for helping you with a particular problem. So, okay, take a look at this next thing here on the next page, which is a little strategy that is this Lyautey. So essentially, if we take a look at the first letter of each one of these categories, each one of these is a specific family of functions. So like logarithmic functions, natural log of x, the log base b of x, maybe log base 10 of x. the common logarithm. Inverse trig functions, algebraic functions, in other words, polynomials. Trig functions, sine, cosine, not the inverse trig, just regular old trig functions, and exponential functions, e to the x, which is what we're mostly familiar with, but also any kind of exponential function, 2 to the x or whatever. This way to think about the functions that you have in your integral will be very useful for integration by parts. Functions that are towards the top of the list, so logarithmic, inverse trig, you should choose for u. Things that are lower in the list, however, you should choose for dv. Now this is a rule of thumb. So again, a rule of thumb basically means that this is a good way to think about things, but it's not necessarily 100% accurate 100% of the time. It's just a guiding principle. Okay. So the reason why you would want to choose these things at the top of the list for you is because logarithms and inverse trig functions have very easy derivatives. For instance, the derivative of the natural log of x is just 1 over x. And even if we have the derivative of some other logarithms, such as the log base 2 of x, this is 1 over x natural log of 2. Very easy derivatives. Inverse trig functions, their derivatives are also very easy. For instance, arctangent, or if you want to write it in that way, this would be 1 over 1 plus x squared. Very easy derivatives. However, if we think about taking an integral here, what is the integral of the natural log of x? Well, that's not actually something that we've learned or talked about in Calc 1. So for the time being, we don't know how to do this. So that would be a really bad choice to make. You would not want to let dv equal natural log of x dx, because for integration by parts, you would have to figure out what this is, and we don't know what this is. So that would be a really bad choice. Furthermore, same thing for arctan. What is the integral of arctangent? That's another thing that we haven't ever talked about. So this would be a terrible choice for dv. So if we think about what would be good choices for dv, we want to pick functions that have easy integrals. So let's just summarize that really quickly. Choose for dv, choose for u, and the reason why you would want to choose these for u is they have easier derivatives. Maybe not easier, let's just say easy. And then for what we have towards the bottom of the list, for dv, these have easy integrals. Of course, right in the middle, we've got polynomials, because to integrate or to differentiate a polynomial is just the appropriate application of the product rule, whether the product rule for integration or the product rule for differentiation. Also, trig functions, their integrals and derivatives are easy. And I would argue that really all of these functions have easy derivatives. None of them really have hard derivatives, but the trade-off here is where do the integrals get hard. These ones up here have very hard integrals, but all of these have very straightforward integrals. So that's why you would want to choose it for dv. Okay, so let's go ahead and we'll go ahead and do example 1 in this intro video as well. So good versus bad choice. So let's evaluate x sine of x, first choosing u equals x, and then again choosing u equals sine of x. So notice here, we want to choose u. The function that we want to pick or assign to u should be functions that are towards the top of the list. So notice that in our integrand here, we've got an algebraic function and a trig function. So this would imply that if we were to follow this scheme, this rule of thumb, liate, we would want to pick u to be the algebraic function and pick dv to be the trig function. So that's exactly what we have for option 1, is to follow Liate, i.e. following Liate, and then for the second time we go about this problem, we want to not follow Liate. We want to pick u to be the trig function, which is lower on the list, which goes against that what's recommended from that rule of thumb Liate. Okay, so let's go ahead and call this 1, and then here we'll do 2. So for number 1, we're going to choose u to be x, and therefore what's left over, dv, must be sine of x dx. Make sure you do write your differentials here. It is important to group them up. So then to find du from u, of course, we differentiate. And then to find v from dv, we integrate. So negative cosine of x. So our integral here, x sine of x dx, becomes u times v, so negative cosine of x times x, which I'll just write it as negative x cosine x, minus the integral of v, which is a double negative, so positive, du, which is dx. So remember, we are doing u dv, and we have uv minus the integral of v du, and just so happens our v is negative, so we get that double negative appearing there. Okay, so the integral that we have showing up is cosine. Well, we know the integral of cosine is sine. So there's our final answer. That was pretty easy. What do we get now if we choose u equals sine of x? Then that means dv would have to be x dx. So to get du from u, we will differentiate. So sine goes to cosine x dx. And v becomes the integral of x, which is 1/2 x squared. So then our original integral, x sine of x dx, becomes u times v minus the integral of v du. And the integral that results is not straightforward. It looks like sort of a slightly more complicated version of the integral we started with. What we started with was a polynomial, an algebraic function, times sine of x, a trig function. So we had an algebraic times a trig. Well, down here we have an algebraic times a trig. Now, sine and cosine, I don't think of them as really one being more complicated than the other, because really sine and cosine are the same function, just one is a horizontal translation of the other. So to me, sine and cosine are like the same function, more or less. Values are different for different input values, but they behave exactly the same way. They're just shifted a little bit. So to me, the presence of this cosine is no different than the presence of this sine. So in that sense, they're the same to me. And then what's slightly different is the polynomial that we have is a degree higher. It's more complicated than what we started with. So this was a bad choice because the integral that integration by parts gave us, the new integral that we have to calculate here, it's more complicated than the integral with which we started. So this was a bad choice. Oops, pardon me. So that's a bad choice. So this leads me to another perspective on integration by parts that I adopted first when I learned calculus. It wasn't later on until I thought of it more as, I began to find it more useful to think of it as, one kind of function times another kind of function. I think that's really good in a Calc 2 setting, Calc 3, differential equations. But the higher up you go in math, if you are to go up and take further higher level theoretical math classes, integration by parts becomes a little bit more, it's a little bit more beneficial to view integration by parts as you've got two functions, and you think of one of them being differentiated and then the other's not being differentiated. And if you want to swap the derivative from one to the other, you can go ahead and do that. So you can see that in the formula for integration by parts. Here, it's sort of like we have the function u and then the derivative of v. And I know that this dv sort of means with respect to, when you see an integral, you usually think of this as meaning the variable of integration is v, and that's one reason why this formula is slightly misleading, and that's why I do tend to like this formula right here. You can rewrite this as the integral of u dv dx equals u times v minus the integral of v du dx. So here you can see we've got two functions everywhere. We've got u. We always have a pair of two things being multiplied together, right? We've got thing 1, thing 2, thing 1, thing 2, thing 1, thing 2. Now what's different in all three of these regions is which function is being differentiated, if at all. So here we can see that this involves the two functions u and v. So you can think of these two as like the before, what really are the two parent functions we're talking about. And then we are looking at the different permutations of derivatives and integrals. So we can take a look at leaving u alone and the derivative of v. Over in this term, we have the derivative on u, and then we have v left alone. So one way I view integration by parts is, which one do I want to be differentiated? Is it more convenient for me to work with this as a dv dx, or is it more convenient for me to leave v alone and work with the derivative of the other term? So it's sort of a way that you can swap which one is being differentiated. And from a perspective of proving things and doing derivations of things and higher level math, I think about that perspective as being more useful. Okay. We'll begin with example 2 in the next video.